So you might have thought that was the end of our derivative rules, and in a sense it was the end of our rules, but we have one technique of differentiation that we need to learn now because there's some functions we don't yet know how to differentiate. In fact, there's a very simple function whose derivative we don't yet know how to take. It's so simple that it only has 2 letters in it. In fact, it's the very same letter repeated twice. The function f of x equals x to the x. Do we know a way to find its derivative yet? So you might be tempted to use the power rule. So the power rule for x to the m, why can't we use the power rule? We can't use the x to the m rule because it only works when m is a what? When m is a constant. So if we had x to the 3 or x to the 1,000, we could use that rule. But we don't have that. You might also think we could use the exponential rule, our b to the x rule. I meant to say rule up here. We can't use the b to the x rule because that rule only works when b is a constant. So we're in trouble here. We need to find a way to take this derivative, but we can't use either of our rules. But guess what will come to save the day? Logarithms. So if we have f of x equals x to the x, I can take the log of each side. ln of f of x is the ln of x to the x. Because we want to be out of this situation where we have the x in the base and the exponent at the same time. So this this is just ln of f of x, but then we have a log rule for this, right? That lets us bring down that x. So we get x ln of x there. And now this is something we know how to take the derivative of, right? We didn't know how to handle x to the x, but x ln of x, that's no trouble for us. That's just product rule. So now we take the derivative of each side. So what's the derivative of ln of f of x? Well, we know that the derivative of ln of something is 1 over the something, but we're not done yet, right? Chain rule says we're supposed to take the derivative of the inside, and in this case, the inside function is f of x, so its derivative is f prime of x. And remember, f prime of x is exactly what we're trying to find. And what rule will we need on the right side? We'll need the product rule. So the derivative of x is 1 times ln of x plus x times the derivative of ln of x, and the derivative of ln of x is 1 over x. Excuse me. And what are we trying to solve for here? We're trying to solve for f prime. So f prime of x is ln of x, and then x times 1 over x just gives us 1, all times f of x. But we actually know what f of x is, right? F of x is x to the x. So the derivative is ln of x plus 1 times x to the x. We could not use our exponent rule, our power rule. We could not use our exponential rule. So whenever you see an example where you have something with an x raised to something with x. So this is not, of course, the only such function. We're about to do another example in a second. This is just the simplest one. So here we've got another one where we've got something with an x raised to something else with an x, meaning our power rule doesn't apply and our b to the x rule doesn't apply. So we need to do logarithmic differentiation. That's what this technique is called. Take the log of both sides first and then differentiate. So I'm going to take the log of this side. That's going to be ln of y. I'm going to take the log of this other side, x squared plus 1 to the sine of x, like that. But this nice property about logarithms, the whole reason we wanted to introduce logarithms, you might remember from week 2, was so that we could bring the exponents out. So now I get ln of y, and I can bring the exponent out front, sine of x, ln of x squared plus 1. So now we've got ourselves out of the troublesome situation where we had x in the base raised to a power that also had an x. So now we know how to take the derivative of both sides. So what's the derivative of ln of y? That's 1 over y. But be careful, don't stop there. I intentionally named this function differently. Back here the function was f of x, and it maybe seemed more obvious that we needed to do 1 over f of x times f prime. This is leading us into something for next week, where we're going to have a lot of y's and x's mixed together. This y is a whole function, right? So I really have ln of some big, long function. So what rule do we need to apply here? The chain rule. So ln of y becomes 1 over y, then times the derivative of y, which we call either y prime or dy dx. I'm going to write it as dy dx. Let's just talk about that one more time. This y is a big, long function. So this ln of y is not the same as just saying ln of x. Because when we have ln of x, x isn't standing for anything other than x. This y is standing for a whole function. So you really have one function inside of another function. So we get ln of y, the derivative of ln of something is 1 over the something. Then you're supposed to take the derivative of the inside something, which is where we get the dy dx. And then in any one of these problems, just like we did in the first example, you're always going to have a multiplication here, so we're always going to have to use the product rule. So the derivative of sine of x is cosine of x. We leave the other part alone. Then we leave the first part alone, sine of x. And now we've got ln of x squared plus 1. So we use our chain rule. The derivative of ln of something is 1 over that very same something. Chain rule says we're not done yet, though. We have to take the derivative of the inside. The derivative of x squared plus 1 is 2x. Are we done? We're not done because we're trying to solve for dy dx here, right? So I'm going to multiply the y to the other side. We can clean this all up into one single fraction here. Put a 2x sine x on the top over x squared plus 1. And then this is all times the y that I multiplied over, but we know what y is. Y is x squared plus 1 raised to the sine of x. And let me just say this now. What's wrong? There's something wrong with this, right? So everything is perfect except that it's going to be a half-point deduction on an exam. What's the trouble here? We're missing some parentheses or brackets, right? We were supposed to multiply this by all of this stuff. But the way that you would read this now is this is only multiplying by this term. We need to put all of this stuff in brackets like that. So that's the derivative of that. So let's just write out how we know that we're going to need to use this technique. We need logarithmic differentiation. What is the situation that caused us in both of these problems to have to take the log both before we took the derivative? It was the fact that we had a function with an x in it raised to another function with an x in it. So we need logarithmic differentiation when we have one function of x raised to another function of x. Because our rules do not apply there, our standard, the rules that we already had. One function of x raised to a function of x. Could be the same function, right? In the first example, they were both x. So please watch out for this. It's very easy to get just in the habit of applying chain rule, chain rule, chain rule, using either the power rule or the exponential rule and not notice this. But those rules don't work. So if you're tempted to just somehow bring the sine of x down and subtract 1 and do something, that's completely illegal because you're using the power rule, and the power rule only works when you have a constant as the power. And sine of x, we know, is not a constant. Now here's just one oddity. Let me just make a remark here. Feel free to ignore this. But suppose that we had this problem here, f of x equal f of x is x to the x. So there was a student once upon a time. Have you heard of this student? This student saw the exam. On the exam, he saw this problem, and he was asked to find what's f prime of x. And the student said, all right, well, maybe I'm supposed to use the power rule. So the power rule I would bring down the x, and then x to the x minus 1. You know better. You know you're not supposed to do this. And the student rule said, oh, okay, well, at least, I don't know if this is right. This doesn't seem quite right, but let me at least try to get some partial credit by showing that I know my exponent rules. This is x to the 1, x to the x minus 1. I know I'm supposed to add those together, so that will just become x to the x. At least the teacher should give me some partial credit for knowing my exponent rules, even though it's a calculus class. But then the student's saying, wow, so that means this function is its own derivative. I seem to remember the teacher saying something about e to the x is its own derivative. So is it really possible that this is its own derivative? That doesn't seem quite right. So we said maybe, or does f prime, maybe I wasn't supposed to use the power rule. Maybe I was supposed to use the exponential rule, where I start with x to the x, and I take ln of x. Maybe that's right. You know better. You know none of these is right. We know the right answer over there. Then the student is sitting there saying, gosh, I don't know which one of those is right. I don't know which one to pick. I'll tell you what I'm going to do. I'm just going to add them together. Who knows what could happen? So this is going to say the answer is x to the x ln of x plus x to the x. I'm going to add my two answers together. Who knows? The exam's almost over. I'm just trying to get a few points of partial credit. Oh, look, I can factor out an x to the x. Surely the teacher will give me partial credit for factoring out an x to the x. So what's left from this? ln of x. What's left from this? 1. How did this student's answer, obtained by doing completely bogus things all the way through, compare to the right answer? It was exactly the same. So please, do not try this on your own. If you want to understand why this works, you can try to come up with a general rule for this, like we came up with a general chain rule. Make up a generic function, call it f of x raised to the g of x. Apply this technique legally to come up with a real formula for the derivative of f of x raised to the g of x that is going to involve f's and f primes and so forth and g's. And then you will understand why, through blind luck, this probably apocryphal, non-existent student managed to get the right answer by doing things completely illegal all the way through the problem. And now we have a check your understanding for you to practice logarithmic differentiation. And next week, we will move on and we'll start using all of these derivative rules in a variety of different things to do useful applications.